Welcome to the Platform Engineering Playbook podcast, where everything you hear is built, reviewed, and improved by AI, by me, and by you, the listener. This show keeps me, and hopefully you, up to speed on the latest in platform engineering, SRE, DevOps, and production engineering. It's a living experiment in how AI can help us track, explain, and discuss the fast-moving world of infrastructure. Every episode is open source. If you've got something to add, correct, or challenge, head to platform-engineering-playbook.com. You'll find all the content and a link to the GitHub repo. Open a pull request, join the conversation, and make the playbook smarter. Let's get into it.
Welcome back to Kubernetes Production Mastery. In Episode 1, we established the production mindset and learned the 6-item production readiness checklist. Before we dive into today's topic, try to recall, what is checklist item number 3? That's right, RBAC least privilege. And here's why this matters more than you think. RBAC misconfiguration is the #1 Kubernetes security vulnerability in production environments. Not 0 days, not container escapes, human error in access control. Last month, a Fortune 500 company experienced a breach. An attacker got access to a single ServiceAccount token with cluster admin permissions. Within 20 minutes, they had pivoted across 47 namespaces, exfiltrated database credentials from secrets, and deployed crypto miners on every node. The root cause? One line in a role binding that gave cluster admin to the default service account. One line. Millions in damages. Today in Episode 3, we're covering security foundations, RBAC, and secrets management. By the end of this 18-minute lesson, you'll be able to implement namespace-scoped RBAC roles that follow least privilege, secure your secrets using sealed secrets or external secrets operator, and identify the 5 RBAC misconfigurations that consistently cause breaches. This is production security that actually works. Let's get started. This lesson will prepare you to write RBAC policies from first principles, not copy-paste from Stack Overflow. Choose the right secrets management solution for your environment, and audit your cluster's RBAC to identify privilege escalation risks before attackers do. Let's start with why. Why is RBAC the #1 security issue when it's been in Kubernetes since version 1.6? Here's what I've seen consistently across organizations. Complexity overwhelms. You're juggling roles, cluster roles, role bindings, cluster role bindings, service accounts, users, and groups. The matrix of possibilities is overwhelming. So engineers default to cluster admin and move on. It works, ship it. But here's the insidious part. RBAC failures are invisible by default. When your pod can't pull images, you see image pull back off immediately. When your pod has excessive permissions, silence. Nothing breaks until it's exploited. And third, development habits bleed to production. In dev, you're the only user with full access. Works fine. But that same everything has admin mindset in production, disaster waiting to happen. In production, you're not asking, does it work? You're asking, what's the blast radius when this gets compromised? That's the mindset shift. Let's build a mental model of how RBAC actually works. 4 components, 1 flow. Oh, no. Component 1, subjects. Who needs access? Service accounts for pods and workloads. That's most of what you'll configure in production. Users for humans accessing the cluster with kube control, and groups for collections of users like system masters. Component 2, resources. What do they need access to? Pods, services, deployments, secrets. Also includes sub-resources like pod/logs or deployment/scale. Component 3, verbs. What actions can they perform? Get, list, watch for read operations. Create, update, patch, delete for write operations, and the wildcard asterisk means all verbs, which is dangerous, use sparingly. Component 4, scope. Where do these permissions apply? Namespace-scoped with role plus role binding, that's preferred, or cluster-scoped with cluster role plus cluster binding, Dangerous, use sparingly. Here's how it connects. You create a role defining resources and verbs. You create a role binding connecting that role to a subject. When the pod tries to perform an action, Kubernetes checks, does this service account have a role binding? What role is attached? Does that role allow this verb on this resource? If yes, allow. If no, deny. Think of it like a building access system. The role is the permission template. Can enter floors 1 through 5, can't enter server room. The role binding is giving someone a key card with those permissions. The subject is the person or pod using that key card. Now here's the most important RBAC decision you'll make: namespace-scoped or cluster-scoped. Let's say your payment service pod needs to read secrets in the payment namespace. You create a role in the payment namespace allowing get and list on secrets. You create a role binding in the payment namespace connecting the payment service account to that role. Blast radius if compromised? Just the payment namespace. The attacker can't pivot to the database namespace or the logging namespace. They're contained. Now, watch what happens with cluster-scoped permissions. Same scenario, but you use a cluster role. Your payment service pod gets access to secrets in every namespace. If compromised, the attacker can read database passwords from the database namespace, API keys from the integration namespace, everything. Blast radius, your entire cluster. Ask yourself, does this workload need cross-namespace access? If yes, and that's rare, use cluster role but minimize verbs. Never use the wildcard. If no, and that's 99% of cases, use namespace-scoped role. Always. Production role. If you can't articulate a specific reason for cluster role, you don't need it. Every pod runs with a service account. If you don't specify one, Kubernetes uses the default service account in that namespace. Here's the trap. If you give permissions to the default service account, every pod in that namespace gets those permissions. That logging sidecar? Cluster admin. That metrics exporter? Cluster admin. Everything. Production pattern. Create a dedicated service account per application. You create a service account, name it Payment Service SA in the payment namespace. Then, in your deployment spec, you explicitly set service account name to Payment Service-SA, not default. Now, permissions are isolated. Your payment service has its permissions. Nothing else does.
Auto-no. 3 anti-patterns to avoid. 1. Wildcards. If you're setting API groups, resources, and verbs all to asterisk, that's cluster admin. You've given up on RBAC. 2. Auto-mounting tokens everywhere. By default, service account tokens mount into every pod at var run secrets, kubernetes.io, service account. If your pod doesn't need Kubernetes API access, disable this. Set auto-mount service account token to false in your pod spec. No token, no API access, no token theft attack vector. 3. Never bind anything to the system masters group. It bypasses all RBAC checks. It's a backdoor. Let's think like an attacker. If I compromise a pod, how do I escalate? Attack pattern 1, token theft. I get shell access to your pod. I read var run secrets, kubernetes.io, serviceaccount.token. Now I have a valid token. If that pod has excessive permissions, I can use kube control with that token to pivot across your cluster.
Auto-no. Defense, disable auto-mount if not needed. Use namespace-scoped roles. Attack pattern 2, privilege escalation via create permissions. Your pod has permission to create role bindings. I create a new role binding giving myself cluster admin. Now I have full cluster access. Defense, never grant create on role binding or cluster role binding unless absolutely necessary. That's privilege escalation as a feature. Attack pattern 3, secrets enumeration. Your pod can list and get secrets. I iterate through all secrets in the namespace, exfiltrate database passwords, API keys, certificates. Defense, grant get on specific secret names, not all secrets. Use field selector limitations when possible. When I audit RBAC, here's what I look for. Are there any cluster role bindings? Why? Can they be namespace-scoped? Does anything have create permissions on roles or role bindings? Are service account tokens auto-mounted into pods that don't need API access? Does any service account have access to secrets it doesn't strictly need? Those 4 questions catch 90% of RBAC issues. Pause the audio. Before we move to secrets management, test yourself. What's wrong with binding permissions to the default service account? When should you use ClusterRole instead of namespace-scoped role? Recall from Episode 1, what is RBAC in the production readiness checklist? Secrets in environment variables. You set env with name, db password, and value supersecret123 right in your manifest. You just committed your database password to Git. It's in your container image. It's visible in kube-control describe pod. It's in your CI/CD logs. It's everywhere. Secrets in config maps. Config maps are for non-sensitive data. They're not encrypted at rest by default. Putting passwords in config maps defeats the purpose. Base 64 confusion. Engineers think Kubernetes secrets are base 64 encoded, so they're encrypted, right? No! Base 64 is encoding, not encryption. Anyone with get secrets permission can decode them instantly. Kube control get secret DB creds. Output the password field, pipe to base 64 -D. Plain text. Here's the core problem. Kubernetes secrets are better than environment variables, but they're still stored in etcd. If your etcd isn't encrypted at rest, your secrets are plain text in the database. If an attacker gets etcd access, game over. Use config maps for application configuration, like feature flags and timeouts, non-sensitive URLs like API endpoints, public certificates, anything you'd be comfortable posting on Stack Overflow. Use secrets for passwords and API keys, database connection strings with embedded credentials, TLS private keys, OAuth tokens, anything that grants access to resources. The test? If it were leaked publicly, would you need to rotate it? If yes, it's a secret. You want Git ups. You want all your manifests in Git, but you can't commit secrets to Git. That's a security violation. Sealed Secrets solves this. Encrypt secrets before they go to Git, decrypt in cluster only. Here's how it works. The Sealed Secrets controller runs in your cluster. It has a private key. It watches for sealed secret resources. The kubeseal CLI runs locally. You run this. It has the controller's public key. It encrypts secrets. The flow. You create a normal secret manifest locally. Never commit this. You use kubeseal to encrypt it. Kubecontrol creates secret generic DB creds. With your password, dry run client mode, output to YAML, pipe to kubeseal, output to sealedsecret.yaml. The sealedsecret.yaml is encrypted. Safe to commit to Git. You apply sealedsecret.yaml to your cluster. The controller sees it, decrypts it with its private key, and creates the actual secret. Your pod reads the secret normally. Think of it like a locked safe. You put your secret in a locked safe, the sealed secret, before storing it in the warehouse, which is Git. Only the in-cluster controller has the key to open that safe. When to use sealed secrets. Best for GitOps workflows where you want all infrastructure in Git, including secrets. Limitation. Secrets still end up in etcd. If your threat model includes attacker has etcd access, this isn't enough. Sealed Secrets puts encrypted secrets in Git, but the decrypted secret still lives in Kubernetes. What if you want secrets to live in a dedicated vault? Pull them into the cluster just in time. That's External Secrets Operator. The External Secrets Operator runs in your cluster. It watches for external secret resources. Your external secret store could be AWS Secrets Manager, Google Secret Manager, HashiCorp Vault, Azure Key Vault. The flow. You store the secret in your external vault, like AWS Secrets Manager. You create an external secret resource in your cluster. You specify which secret to pull from AWS, which Kubernetes secret to create. The operator pulls the secret from AWS Secrets Manager, creates a Kubernetes secret with that value, and your pod reads it normally. Key advantage. Secrets never live in Git. Secrets are centrally managed in your vault. Rotation happens in one place, the vault. Kubernetes stays in sync automatically. Plus, your vault has better access control, audit logging, and encryption than etcd. When to use External Secrets Operator. Best for organizations with existing secret management infrastructure. Best for high security environments where secrets in etcd is unacceptable. Limitation. Adds dependency on an external system. If the vault is down, new pods can't start. 3 common mistakes. 1. Login secrets. Your app logs connected to database with password supersecret123. pause, long. Congratulations, your password is now in CloudWatch, Splunk, or Elasticsearch forever. Fix, sanitize logs. Never log secrets. Ever. 2. Secrets in error messages. Your connection fails. The error? Failed to connect using postgres//user.supersecret@. Fix. Catch exceptions. Log a generic error. Don't expose connection strings. 3. Overly broad secret access. Every pod in the namespace has get permission on all secrets. Fix. Grant get on specific secret names only. In your role, rules set resources to secrets, but add resource names with just the secrets that workload needs, like DB creds. Set verbs to get only that secret.
Pause and test yourself. Why is base64 encoding not encryption? When would you use sealed secrets versus external secrets operator? What's wrong with env name password value secret 123?
AutoNo misconfiguration 1. Cluster admin for workloads. Search with kubectl get ClusterRole bindings output to YAML. grep for cluster admin with 5 lines of context. Look for ServiceAccounts bound to cluster admin. Fix. Use namespace-scoped roles instead. Misconfiguration 2. Wildcard permissions. Search your roles for resources equals verbs equals asterisk or look for overly permissive rules. Fix. Specify exact resources and verbs needed. Misconfiguration 3. Default service account permissions. Search for any role binding with name default in the subjects. Look for permissions granted to the default service account. Fix. Create dedicated service accounts. Misconfiguration 4. Create permissions on RBAC resources. Search for roles allowing create on roles or role bindings. Look for privilege escalation paths. Fix. Remove unless absolutely needed. Tightly scope. Misconfiguration 5. Auto-mounted tokens in non-API pods. Search for pods without auto-mount service account tokens set to false. Look for unnecessary token exposure. Fix. Disable for pods that don't need Kubernetes API access. Remember episode 1's production mindset? What happens when this is compromised? That's what RBAC and secrets management are about. Not if your pod gets compromised. When. When that happens, namespace-scoped RBAC limits the blast radius. Dedicated service accounts isolate damage. Sealed secrets or external secrets prevent credential exposure. Disabled token auto-mount removes attack vectors. This is defense in depth. Every layer makes the attacker's job harder. This is checklist item number 3 from episode 1, RBAC least privilege. Now you know how to implement it. Let's recap episode 3. Part 1, RBAC. RBAC has 4 components: subjects, resources, verbs, scope. Always prefer namespace-scoped role over cluster role. Create dedicated service accounts per application, not default. Disable token auto-mount if the pod doesn't need API access. Watch for wildcards, privilege escalation, and token theft. Part 2, secrets. Base 64 is encoding, not encryption. Use secrets for sensitive data, config maps for configuration. Sealed secrets. Encrypt before Git, decrypt in cluster. External secrets operator. Pull from external vault, never in Git. Never log secrets. Sanitize errors and scope secret access tightly. The 5 misconfigurations. Cluster admin for workloads. Wildcard permissions. Default service account permissions. Create permissions on RBAC resources. Auto-mounted tokens everywhere. RBAC misconfiguration is preventable. The Fortune 500 breach I mentioned? Preventable. The patterns you learned today prevent it. Security in production isn't about perfection. It's about making the attacker's job so hard they move to an easier target. That's what Defense in Depth achieves. Next time, Episode 4, Troubleshooting Crashes, Crash Loop Back Off, and beyond. You'll learn the systematic troubleshooting workflow for pod failures, how to diagnose crash loop back off, image pull back off, and pending states, and how to configure health checks that actually prevent failures. We're taking failure pattern number 3 from episode 1 and giving you a complete debugging playbook. Troubleshooting is a skill, and we're building that skill systematically. I'll see you in episode 4.
That's it for this episode of the Platform Engineering Playbook podcast. Every topic, transcript, and summary you just heard lives out in the open at platform-engineering-playbook.com, where anyone can suggest updates or add insights through GitHub. If you've got thoughts, fixes, or new ideas, open a PR. And if you enjoyed the episode, rate us on your favorite podcast platform. We're always shooting for 5 stars. While you're there, give the project a star on GitHub. It helps others find and contribute to the Platform Engineering Playbook. This podcast is generated by AI, reviewed by AI, me and you, a community of engineers keeping our craft sharp. Thanks for listening, and see you next time inside the Platform Engineering Playbook.